Let's know what the problem is.
Okay, so I think that the problem is like U and V are rational, right? Wait, UV. Wait, oh no.
Do you know the definitions of it? Yeah. Yeah.
Why is there a ruler?
Oh, what?
Hmm. Why doing that? The ruler isn't even there. Oh, stop. Oh wait, they actually let you draw circles? That's crazy.
Wait, is it an update?
I don't know.
Believe it or not, we have to pay for that one.
That's crazy. Okay. The N6 was like
there forever, like it doesn't get deleted. Oh, when you link it. Yeah. That link should work according to that.
when you see the question, where was it?
You're on my laptop, but
It's here, wait, no, somewhere.
yeah, it's got it.
So. Okay. U and V are different positive rational numbers.
Spencer's got it on the laptop. Can like have that open.
Okay. Yeah, okay, they're positive rationals. And they are different, distinct. Okay.
So different positive rationals U and V.
And then there are infinite n.
Infinitely many powers.
And so then U to the n minus V to the n is an integer. Okay.
What's that?
Prove U and V are also integers. Okay.
That's a nice little question.
So then I was like, I was like, okay, I'll just write U and V as fractions to deal with the rational part of it. I'll just let U equal A on C and then V equal B on D or something. I don't know. Okay. And then if that is okay, but I want A and C to be co-prime. I kind of want it to be like the most reduced form of the fraction. Similarly, B D co-prime.
Co-prime is kind of bro.
I just want them to be that so that it's nice.
Definition question.
I guess
Yeah.
I didn't really prove this, but like rationals have unique ways of expressing them in this form, A and C co-prime B and. But I didn't prove it, and I actually don't know why it's true. I never bothered with it. I've never bothered with it. It was just an assumption I always made, but then like I realized, wait, I don't actually. Okay, anyways, well, moving on. So then I wrote U to the n minus V to the n. Then that would equal the A to the n over C to the n minus B to the n over D to the n. And notice how A to the n and C to the n are still co-prime. And same thing with B and D, B to the n, D to the n. So that's pretty cool. So then, yeah, basically the point is that they're still co-prime, so they still have this property of being the most reduced kind of thing. So then, what did I do? I think I did like, let's see. So then I moved it around a bit, so it was like, I don't know, I guess I'll let them equal, like, I don't know, m. I'll let this equal m. So, yeah. And then I wrote it as, yeah, so then I wrote it as like U to the n equals B to the n on D to the n. Wait, hold on. Wait, what did I do? I did. Okay, nah, that's skipping a step which is gonna be very confusing. I'm gonna not skip this step. It's equals b to the n plus n equals b to the n. I think then I just put them on the common denominator. Okay, so I think the move to make here is that since b to the n and d to the n are co-prime, then m times d to the n plus b to the n over d to the n, they're also co-prime. Because you're kind of adding a multiple. It's actually, I didn't exactly write this down, but basically, like, let's assume that for the sake of contradiction that these two aren't co-prime for some reason, then I guess they share a common factor. So then let that factor be like, I don't know, x. X divides m times d to the n plus b to the n. And then x divides d to the n. But then if you subtract the d to the n from here, like m times, because that's how divisibility works, then x divides b to the n, that's a contradiction, because these both divide.
Yeah.
And we assume that these were co-prime. So therefore, this fraction this fraction is in its most reduced form.
Yeah.
So that fraction is also equal to, because it's equal to u to the n, so it's a to the n over c to the n. So then c to the n equals d to the n, because I had claimed earlier that there's a unique representation, but I never actually proved it in my life, which is a slight issue, but...
Can you just find that?
Well,
I think yeah, it's well accepted. So
it's well accepted, but I never proved it, so I don't know. Maybe that's something to do later. Alright, so then I just, since c to the n equals d to the n, and then like everything's positive, so just c equals d. So I'll just write everything from now on as I'll change the u equals a over c, I'll change it to d. There we go. So now a and d are, because c equals d, so.
Wait, what does that? Oh, you just, okay.
I proved c equals d.
Okay.
Okay. Well, assuming that there exists an n that works, then a c equals d. Oh yeah, that would be better. It's just like, boom, d.
Yeah.
Alright.
Now we've done the original question with d.
Yeah. So obviously we're assuming there's infinitely many n, so there has to be at least one n, which is why this works. So I just put one of the n in here. But like, if there were no n, then I couldn't do this. But obviously I'm assuming there's infinite. Okay, so
just one n is enough to get the denominators the same.
Yeah. Just like the existing
one
n.
Haven't even fully used.
Okay, so now I do the. Now I just put it in here, right? So use that was v to the n. Okay, now I cross this out as d to the n again. Oh, the denominators are equal. So now we get, okay, actually no, I'll just keep it red. It goes a to the n minus b to the n over d n. It's pretty interesting. So now we managed to turn the u to the n okay, into this fraction. So yeah, so obviously you can see if d equals 1, then this is going to be an integer automatically. And d equals 1 if and only if like they're both integers.
Doesn't d have to equal 1 though?
Oh yeah, well we're supposed to prove that it equals 1, right? So I assume for the sake of contradiction that d is not 1. So let's do d is not 1. And then see what happens. So
this would be like an
yeah, okay. If d is not 1, then I actually simplified it a little bit because yeah, because the thing is, right, d can be like any number, but notice how, according to the question at least, like we can make d anything that's not 1, it won't work. There won't be infinitely many n. And so I guess the weakest form of that is if D is a prime number, because if D is a prime number, then it's kind of like it has to divide into A to the n minus B to the n the least, and then get an get an integer. So I think basically what I did, I let P divide D. There's P that divides D. Exists P divide D, where P is prime. And you can see that if A to the n minus B to the n over D to the n is prime, or is an integer, then if you replace D with P, that's still gonna work. So then I just turn it.
D is prime.
Effectively, I'm logging it, yeah. But yeah, basically, like, if there exists infinitely many n so that this is an integer, anytime that this is an integer, then this is also an integer, because P divides D, so we're basically just like, yeah, so, yeah, basically, if there's infinitely many that where this is an integer, then there's infinitely many where this is an integer as well.
That'll be enough to get a point.
So, I think that's what I did.
We heard the phrase log, but we have without loss of generality.
Yeah.
Yeah. So it appears that generality is lost because you're proving it for E instead of D.
Yeah.
Which is a special case.
But it's still fair to prove it because it's like.
Yeah, because I'm able to take this P. So, yeah. So now it's getting a little bit more like traditional number theory. Because now we get that P to the n divides A to the n minus B to the n.
Oh,
Sus. Okay, now I'm going to do the move. I'm going to do the thing.
Oh.
Yeah, I did the thing.
So that's similar to mu.
So basically, like this mu thing, mu subscript P. That's basically just how many P's there are in A to the n, B to the n. So like if you take the prime factorization of A to the n minus B to the n, you take like the exponent on P. That's this thing. That's what this represents. That's what this represents. Yeah. And so obviously if P to the nth power divides A to the n minus B to the n, then the power of P inside A to the n minus B to the n has to be at least n. So it doesn't, so it actually divides. So that's what we do.
Also, that's the amount, that's the power of the prime factorization of P. It's bigger than or equal to n.
Yeah. So there's actually this thing called the lifting the exponent level. Yeah, I think there's like a few things missing from my proof because they're actually like sus parts. Alright. So the lifting exponent states that VP of A to the n minus B to the n. Okay, so this relies on A and B not being divisible by P, I think, which is true because A and D are, and B and D are co-prime. So P cannot be a factor of A or B. So, but if that is true, and so A and B is not divisible by P, then VP of A to the n minus B to the n for odd P, I think odd P, is equal to VP of A minus B plus VP of N. I think for P equals 2, which is like the even thing, there's like something slightly different.
Yeah.
I think.
吓死我了！我也把他压死了呢。
Wait, I think. You know what? Let's just search this up because I actually forgot. Okay, what is it?
V of 2xn minus yn is equal to V of 2 of x minus y plus V of 2 of x plus y plus V of 2 of n minus 1.
Okay. Wait. So A minus B, A plus B.
That's if n is even.
P equals 2, n is even.
Yeah. if n is odd, it's just b of 2 of xn minus y and b of x minus y.
Wait, what was that again?
If n is odd, you just get b2 of xn minus yn is b2 of x minus y.
X minus y, just this. Really?
Yeah, it is. Ultimately, it is.
And so where the n is this.
Yeah.
Odd p.
Wait, so X minus y, I'll just replace this with A and B.
So, yeah, the first time.
Let's have a look at this.
And this is how that's why it's okay.
Yeah.
Go on Wikipedia.
That's just what I did. Like just like
Yeah. 2x minus y. Okay.
X minus two.
Yeah. Actually, I haven't in my.
没有拿了，你还去
Yeah, so the way they get kind of, this is a
拿
rough
下
idea.
来，没看到吗？
This thing's
It's quite the interesting.
if you assume
The amount of powers of that.
you assume P divides A minus P.
不能用那个。
And once you get the statements of what that effectively solves the problem.
Yeah.
Because
很危险。
you can
It's
basically
just the bound.
sorry, because you can ignore the VP of x minus y, the V2 of x minus y, and V2 of x plus y because it's constant.
Mhm.
You just
Yeah, it's
get-
just n. Right?
Yeah, you just get the
So like
VP of
by the informatics
yeah.
techniques, you get like log versus linear.
You basically get p has to be 1 for it to be true.
Yeah. And
Hmm.
then
Well, P is not 1, but like
Yeah.
I assume that D is not 1, so
Yeah. So that gives
then I
you-
get a P.
yeah.
That's roughly the idea. But you have to put more.
Yeah, and then because the amount of factors in P of this is the amount of factors in P of
Okay, so I think basically if n is odd, then it equals this. But basically what I did was I don't care that it just says this because n is odd, which means that I'm just gonna add on the VP of n because VP of n is 0 if n is odd because 2. So I basically just made it the same as this case. We only have to take care of the even case, but like, okay, so the general concept that Liam has mentioned is that obviously we're trying to vary n and then find like all of the different n that work. But so, and we want VP, well, we want this thing to be greater than or equal to n. Notice that if we vary n, right, this VPs a minus v and a plus b and this minus 1, they stay constant. They just stay constant. But then we have, all we have is just plus this VP of n here. So yeah, it's kind of like a linear equation in terms of VP of n. It's pretty funny. But pretty much, it's like, can VP of n even grow as fast as n does?
No.
Yeah, it's like, so if, let's have a look. Yeah. So basically like, p to the, wait, yeah, p to the VP of, I think it's like this, right? Hold on, let me check. Yeah, it's new, but like V, it looks like a V, so I don't care. Like, I think in my document I typed as new, but like, it just doesn't make sense. Alright. It's like P VP of and divides. I think that's true. Like,
Yeah.
yeah, in all these cases.
Yeah, VP of n is always less than
Divides.
Yeah.
I think that's how it works. So let's check if that's true in all these cases. So
Yeah.
as you can see, this is here VP of n is less than or equal to this thing. So therefore, it is true.
It may not be true in the 2 case.
In the 2 case, no, just wait.
The -1 is different.
Oh, the minus. Hold on, let me check. So if n is even. Let me see.
你可以吃饭了。
So. Yeah.
等它结束就
Oh no. Okay, so
It's always true.
no, because like basically, if p equals 2, then a and b have to be odd
Yeah,
because we said it was co-prime.
that's true.
So then these two both have to be like at least 1.
Yeah.
So that cancels out with the -1, which means that v2 of n is less than or equal to this. Okay, so I think that's what we get, right? Yeah. So if that is true, like something can only divide something else if it's like less than or equal to it.
Yeah.
It's like to the is that how it works? Wait, hold on. Let me read what I think I did it in cases though, so this wouldn't be my original. Yeah, this definitely wouldn't be equivalent to my original. Okay. So, I did this. Okay, what the hell? It's so weird. So, I let k. I defined a k. Right? So k, let k equals the maximum of VP minus. Okay, VP of a minus b. So I basically like lumped all the constant stuff from all of these equations into one thing, and I took the maximum of them because I basically want to make sure that k is, I guess k is at least the constant parts in each of these equations. And so then k plus vp n is at least this thing. Okay, and then as you can see, this is greater than or equal to n. So this thing is greater than or equal to n. So then yeah, k doesn't depend on n. So then I rearrange it a little bit.
Oh, in case.
K, and then yeah, so then n p to the n minus k divides divides n.
Wait, is that step already something sus? Like u of n is greater than equal to n minus k? So anything
It's k. Really? How's this sus?
It's implied.
Oh, it's basically just like this is greater than this.
Yeah. The number of p's in n.
Ooh.
It's like saying if you have like e to the 6, right? It's like saying 6 is greater than equal to p to the 6.
6 is greater than equal to. Yeah. That's basically the whole point of this.
So that's like contradict. That's the.
Yeah, like it doesn't really make. It just doesn't make any sense. Like, how could p to the n minus k be less than or equal to n for arbitrary large n? Like, just doesn't make sense.
Yeah. It's like essentially like log is saying log is bigger than n.
Yeah, which is not true for sufficiently large. So if that is the case, that's basically the sus part that I didn't really talk about properly. I was just like, yeah, it grows large enough. But like I didn't really prove that this would eventually not work. But yeah, that's the basic idea. Yeah. Hmm.
M minus K is less than equal to A.
Yeah.
Which is not true.
Hmm.
Yeah. It's not true for infinitely many X. Yeah. It might be true for some small N.
Yeah.
Yeah. Something like usually like something like lifting the X-Men, it wouldn't be essential, but it would make it easier. See, like
Yeah.
Alright guys, let's clear this table. Thanks, Alex.
And